of this time and go over things. Okay? We'll most likely start the quiz early. If you finish the quiz early and you want to go over homework while other people are finishing up, we can quietly do that. Okay? We need to take advantage of the time that we have. The rest, for the bulk of the rest of the semester, not every week, but we are going to finish, we're in less of a time crunch the rest of the way up. Okay? And that's on purpose. We're really trying to focus on that final exam. Okay? Not teaching to the test, but keeping in mind that we have that cumulative final exam coming and doing everything we have to make sure that you remember everything from the course. If you remember everything from the course, you will do well on the final. Or if you look at it the other way, if you study for the final so that you will do well on the final covers everything in the course. So if you study to do well on the final, that means that you know everything in the course. So that's the view that we're going to take from here on out. Okay? So today we're going to talk about solutions. And if you are one of the people in here, I think most of you are, that are in some sort of a pre-health field, in my mind, solutions are probably the most relevant part of chemistry to you. Okay? Solutions are the part of chemistry that I use every single day in lab. Multiple times, probably dozens of times in lab. And that's because life is a big bag of solutions. Every cell in my body is a little bag containing solutions of different things. And that's what makes life go. So if I'm working in the lab, I'm working with solutions. I'm replicating life in the conditions that are in a body in a test tube. So I'm constantly working with solutions.
Are we able to turn off that light?
We can. I've been turning it on because people were saying that the glare with it off, the glare from this hits here, and it's hard to read the Sharpie on the board.
Yeah.
What's your preference?
You can't read it with the light on.
You can't read it with the light on either?
Not really, you really can't see it the way I don't.
That's,
Right there. That one.
maybe that one? Let's try that one. So the first week of class, we talked about different types of mixtures. And at that point in time, we said that there were 3 types of mixture. Well, we said there were homogeneous mixtures, and then there were heterogeneous mixtures. Today, we're going to break this down a little bit further. So if we're talking about mixtures in a liquid, where we have a liquid, and then we put a solid in that liquid. So we have a mixture of a solid and a liquid, we can end up with one of 3 things. A suspension is just the solid suspended in the liquid, and it's probably temporary. Imagine you have a glass of water, and on the bottom of that glass is sand. And then you take a spoon and you stir it up. What's going to happen to the sand in the bottom of that glass? It's going to move up. It's going to come and get suspended in the water. That is a suspension. But if I stop stirring, what happens to the sand?
Stops.
It settles. So a suspension is something where the solid will settle out. It may take longer. The sand is going to settle very fast. Imagine we go out and we find a lake. And I take a water sample of that and I set it on the bench. And I come back 5 minutes later, it's probably going to look exactly the same as it did. But if I come back 24 hours later, something probably will have settled out of that. That is still a suspension. On the opposite end of a suspension is a solution. We'll come back to this one. A solution will not settle out. The solid is completely dissolved in the liquid. And we'll talk about what we really mean by dissolving, but you already have an idea, you have a picture in your mind of what it means for something to be dissolved in water. So if I take that same glass of water, instead of sand, I put salt. You know what that's going to look like if that salt dissolves, right? If I put a bunch of salt in there and I stir it, before it's all dissolved, I'm going to have a suspension. But eventually it's going to disappear. The salt is going to become completely invisible. It's going to be dissolved in the water, and no matter how long I let it sit here, nothing is going to settle out. In between the two, between the suspension and the solution, is what we call a colloidal suspension. This is probably something you will never run across in real life. Okay? A colloidal suspension is a suspension where the little particles are so small that they won't settle out. But they're big enough to make the liquid a little bit cloudy. And so, this is hard to see, but here you can probably see it's very cloudy. Can you see that? That is definitely a suspension. And over here, it looks like it's just plain water. That's because all of what's in here, which is probably salt, has been dissolved. And here in the middle, hopefully you can see it, it's a little bit hazy. It's not quite as clear as that. That is a colloidal suspension. To the eye, it's not quite clear. It's not 100% transparent. But if I let that sit, it's not going to settle out. For us, we're concerned about solutions and suspensions. Those are the two that you're going to see in lab. Those are the two that you're going to see on homework, and quiz questions, and the final exam. Okay? But just know that there is this kind of fuzzy middle ground that can happen between them. So, solutions come in a lot of different forms. It's not just a solid dissolved in a liquid. So, in our body, we have a lot of sodium chloride. We have sodium chloride dissolved in water in our body. So this is a solid dissolved in a liquid. But we can also have solutions with gas dissolved in another gas. So this is air. Air is a solution. There is a number of different types of gases in the air, but do you know which type of molecule, which element is most abundant in air?
Nitrogen?
Nitrogen. Nitrogen makes up, I believe it's about 70 to 75% of the air. And so, the air is really a solution of oxygen and argon and carbon dioxide and methane and all of those other types of gases dissolved in nitrogen. And so if you have a patient that is taking breathing treatments, you're probably not going to give them air. You're probably going to give them oxygen. But you also don't give someone pure oxygen. What you give them is sort of like air, but there's just a much higher concentration of oxygen in it than there would normally be. So we have that type of a solution. We can also have a solution of a metal in a metal. So if you have titanium rods in your leg, or titanium screws, that looks very, very painful. But if you have titanium rods, that's not 100% titanium. That is titanium with a little bit of aluminum and a little bit of vanadium in it. It changes the properties a little bit. And so they can tailor, depending on how much aluminum and how much vanadium they put in there, they can change the hardness of it. They can change the flexibility of it. So this is a solid in a solid solution. So by far, the most common type of solution that we deal with is solids and liquids. But That is not the definition of a solution. A solution is one compound dissolved or mixed with another that is homogeneous and will not settle out. When we talk about solutions, we have some definitions that we're going to have to define. We're going to talk about the different parts of a solution. So, solution itself is a homogeneous mixture. That salt water is a homogeneous mixture. There's just as much salt dissolved in the water, top of the glass, as the bottom. That sand in the water is not homogeneous. There is more sand at the bottom than at the top. Pond water is not homogeneous. There's little floaties in there. A solution is homogeneous. In that solution, we have what we call the solute. The solute is the thing that is being dissolved. For the most part, that is the thing that there is the least of. So if you're making salt water, you're dissolving salt in water. Generally, you're going to have more water than salt. The salt in salt water is called our solute. And the water is called the solvent. The solvent is the thing that does the dissolving, and there's usually more of it. You've probably heard the word solvent used outside of chemistry. Like if you're talking home improvement, or if you are dissolving glue or something at home, you might have heard that thing that you use to dissolve the glue called a solvent. So a solvent does the dissolving. For the most part, the solvent is going to be a liquid, and the solute is going to be a solid. Those two words make sense? And then finally we have the aqueous solution. An aqueous solution is just a very specific solution where the solvent is water, which is most of the solutions that we'll be using. So here we have something being poured into something else. Which one of these things is the solute?
Sugar,
Something
whatever.
you put in.
It's the solid that's being poured in. It could be salt, it could be sugar, it could be something else. All right? So what is the solvent? The liquid. The liquid is dissolving the solid. So the liquid is the solvent. You already know that some things dissolve better than other things, right? If I put salt in water, it's going to dissolve. If I put sugar in water, it's going to dissolve. If I put this clicker in water, it's not going to dissolve, right? If I put oil in water, it's not going to dissolve. You know that. The ability of something to dissolve in a specific solvent is called its solubility. If we have an ionic compound, remember that when we dissolve it in something, particularly in water, the ions break apart. So if I dissolve sodium chloride, when it's dissolved in the water, it is no longer sodium chloride. It is now sodium ions and chloride ions. If I put an insoluble compound, so an insoluble means not soluble, an insoluble compound in water will not break apart. So one of the examples that we have done in class is silver hydroxide. That is not soluble. That is insoluble. So if I put that in water, it's going to stay like that. That is insoluble. It's not going to break apart. If you remember that solubility table that we used when we were dealing with the double displacement reactions, there was not necessarily a logical pattern. You had to look things up, okay? And so if you want to find out if something is soluble or insoluble, you have to look it up. It's not predictable. And there are solubility charts, okay? I don't think you're going to have to use a solubility chart around this lecture, but you already know how to use it. Okay, so not only does something dissolve or not dissolve in a solvent, but there are things that will change how quickly it dissolves. Without looking at your slides, what are some things that you already know that you can do to make something dissolve faster? Temperature, what about temperature? What can you do with it?
Increase.
Increase temperature. You heat something up, it dissolves faster. Right? You can stir it, right? So there are three things. Those are the two easy ones. Can anybody come up with the third without looking at your slides? Yeah.
Adding something to speed it up, like adding gasoline to fire.
That would be a reaction, and so that's not by definition dissolve. So we got temperature. The other one is surface area.
Huh.
So imagine you're dissolving sugar in water. You can choose granulated sugar, or you can choose sugar cubes. Which one do you think is going to dissolve faster? Granulated sugar. Nowhere in here did I tell you that increased surface area increases rate of dissolving. But you know that, right? Either by experience, or you can just look at it and see that's going to dissolve. If I put the granulated sugar in the water, it can all dissolve at the same time. If I put the sugar cube in the water, the only part that can dissolve is the outside of the cube. Because in order for the sugar to dissolve in the water, it has to be touching the water. And if I put that cube in the water, the center of the cube isn't touching the water. So the center of the cube has to wait for everything on the outside to dissolve before it can dissolve. And the last one is mixing. So if you make Jell-O, if you try to make Jell-O without heating it up, you're going to be stirring for a long, long, long time, right? And if you ever made Kool-Aid, if you just poured the Kool-Aid in the container and put it in the refrigerator and waited for it to dissolve, you're going to be waiting a long, long time. And if you're making Kool-Aid, you probably were either a kid or you were making it for a kid, and kids aren't patient enough to wait a week for the Kool-Aid to dissolve, right? And so you stirred that Kool-Aid. You didn't have to heat it. You stirred it, and it dissolved. So we can change three things to change the rate of dissolving. We can raise the temperature, we can increase the surface area, or we can stir it. When we dissolve an ionic compound in water, it breaks apart, we said. And if we get ions floating around in water, we get what we call an electrolyte. An electrolyte is a solution that conducts electricity. And there are two types. There are strong electrolytes. These strong electrolytes are ionic compounds that completely break apart. Like when you put sodium chloride in water, it completely breaks apart into sodium and chloride. For us, every ionic compound that is soluble will be a strong electrolyte. Silver hydroxide is insoluble. It is not any sort of electrolyte. It is what we call a non-electrolyte. The opposite, or the middle ground, is below a strong electrolyte, we have weak electrolyte. These are solutes that only partially dissociate. And an ionic compound is not going to do that. An ionic compound is either going to completely dissociate or not dissociate at all. These weak electrolytes are organic compounds. What we'll use as an example in lab is vinegar. Vinegar is a complicated little molecule. It's not ionic like this. It's a molecular compound. It's a molecular compound, but it behaves a little bit like an ionic compound. And so if we put 1,000,000 vinegar molecules in water, 2 or 3 of them are going to dissociate. And so you're going to have a few ions floating around, and so you're going to conduct electricity a little bit. These conduct electricity because of the ions. Electricity is the movement of charges. So if I hook a wire up to one side of a beaker of a solution and another wire up to the other, in order for that to conduct electricity, charges have to move from one wire to the other through the liquid. And here we have charges. That sodium ion and that chloride ion are floating around in that water. If they need to move, they can move. If the chlorine needs to go over to this side of the beaker, it can go. If the sodium needs to go to that side of the beaker, it can go. But if we have silver hydroxide, it's just sitting down here in little chunks. It can't go anywhere. If I have a molecular compound that's dissolved, it is dissolved, but let's say it is methane. Methane is CH4. That does not, it's a molecular compound, it does not break up into ions. So even though it's dissolved, it is a non-electrolyte. It does not dissociate into ions. I believe this is what we're going to be doing in the lab this week. Yeah.
How will we be able to tell if it's what it is?
In the lab, we're actually going to gear test it. And so you'll take it, you'll see if it conducts electricity. If it conducts electricity very well, it's strong. If it doesn't conduct at all, it's non. If it conducts it a little bit, it's weak. So if you're looking at a formula and you need to be able to tell, you should first say, well, is it ionic? If it's ionic, is it soluble in water? If it's soluble in water, it completely dissociates, it's strong. If it's insoluble, it's non. You won't be able to look at a molecular compound and tell me whether it's weak or not. That's not something I would expect you to be able to do. So this is more or less what you're going to do in lab. You're going to have a light bulb with 2 posts, stick the posts into the liquid and see if it conducts electricity. So in order for the light bulb to light up, the electricity has to come in, come down the post, go through the water, up the other post, through the filament, and out. If this water, this solution doesn't conduct electricity, the electricity is not going to be able to go from here to here. You break the circuit and the light doesn't come on. So these are examples of electrolytes. We have hydrochloric acid, we get H plus and Cl minus. Sodium hydroxide gives us sodium and hydroxide, sodium and chlorine, and hydrogen and nitrate. Those are ionic, soluble ionic compounds. When they're in the water, they'll dissociate and the ions will conduct electricity. If you look at the bulk of all, if you look at all the compounds in the world, statistically, most of them are going to be non-electrolytes. And that's because most molecules in the world are molecular compounds. They're not ionic. And so when they dissolve, they're not going to break up into ions. hydrogen peroxide is an example. Hydrogen peroxide, when you buy it in the store, is hydrogen peroxide that's already dissolved in water. You're not buying 100% hydrogen peroxide. When you pour that out, you have the hydrogen peroxide dissolved in the water. The hydrogen peroxide does not break apart. When you dissolve it in water, you go from hydrogen peroxide liquid to hydrogen peroxide aqueous. It did not change its form. So that is a non-electrolyte. So we're going to take these compounds and we are going to write out what happens when we dissolve them in water. So first one is we're starting with zinc chloride. If I dissolve it in water, what am I going to get from that? We will get zinc, and we'll get chlorine. What do I need to do to these? I need to add charges. So what is the charge on the zinc?
Positive.
Positive what? 2. Positive 2. What's the charge on the chlorine?
-1.
Negative 1. Anything else that I need to do?
Balance.
I need to balance it. I have 2 chlorines here, so I'm going to get 2 of those. I am not going to get Cl2. These are 2 chloride ions that once they're dissolved, they're completely independent of each other. And then I need to finish it off by putting my state symbols. They are now aqueous. Go to the next one. We have potassium nitrate, solid. When I dissolve it in water, what am I going to get? I'll get potassium plus
1 plus.
plus nitrate. What's the charge on nitrate?
-1.
Negative 1. Is it balanced? Yes.
Yes.
What else do I need to do?
Oh, you need to write down that's aqueous.
I need to put that they're aqueous.
How do you know that the nitrate is, the charge is negative?
That was one of the ones we had to memorize a while ago. It's on the cheat sheet. Okay, now we got the last one. We've got C2H5OH. This is a liquid. I will tell you, this is a molecular, you know by looking at it, it's a molecular compound. It is not an ionic compound. So when I dissolve this in water, what am I going to get? How would you write that?
They won't break apart, right?
It won't break apart. So if it doesn't break apart, I can just write it out again.
And then put aqueous.
Right. It just goes from C2H5OH liquid to C2H5OH aqueous.
From looking at that compound, how can you tell whether it's molecular or ionic from just looking at it?
How do you tell if something is molecular or ionic?
It's ionic, it's in the metal.
There's no
Or
matter.
As a metal? Oh, okay, yeah, that's metal, okay. I remember.
That's why we got the big homework, so you don't forget that stuff. Alright. So just like there were things that affect how quickly something dissolves, there are also things that affect how well something dissolves. So we said that salt and sugar will dissolve in water, the pointer won't, oil won't. What determines that? And there are three things we're going to look at. We have structure, temperature, and pressure. So structure refers to the atoms that make up a molecule. And so this is vitamin A. This is a very big molecule. We have a whole bunch of carbons, a whole bunch of hydrogens, all bonded together, and all the way down here at the end, there's one little oxygen. This is vitamin C. It looks sort of similar, but it's much more compact. Right? There are a lot less of these carbon-hydrogen bonds, and there are a lot more oxygens. So when you're looking at these molecules, the more oxygens you have, the more polar you are. The more carbons you have, the less polar you are. So if you were going to say which of these two is least polar, which one would you say? Vitamin A. It has more carbons and fewer oxygens. So this one is less polar. Have you ever heard of water-soluble and fat-soluble or lipid-soluble vitamins?
Yeah.
This is what it's referring to. Things that are polar like to dissolve in things that are polar. Things that are non-polar dissolve in other things that are non-polar. So vitamin A is a lipid or fat-soluble vitamin. It's going to dissolve in your body in things that are non-polar. And so if you're going to dissolve vitamin A and absorb it into your body, you're going to need to eat it with something that is non-polar, like fat or oil. You're not going to need much, but if you don't have any, that vitamin A is not going to absorb into your body. Vitamin C is very polar. It dissolves. That's a water-soluble vitamin. If you drink it in the water, it's going to get absorbed into your body. So fat is very, very non-polar. So the blacks and whites here are carbons and hydrogens. So this is a fat molecule. You have a lot of non-polar carbon-hydrogen here. And then up here, at what we call the head, there are a few oxygens. And so fat is non-polar. And so the vitamin A will dissolve in the non-polar fat. So using that, somebody explain to me why oil and water don't dissolve in each other.
Isn't oil like fat?
Oil is like fats. So oil is non-polar. Water is very polar. So you have something that is non-polar in the oil, something that's polar in the water, and so they don't mix, and the oil just sits on top of the water. Why, then, are CCl4 and C6H14 soluble in each other? What can you say about the polarity of those two molecules that makes them soluble in each other? Why do they dissolve in each other?
Those are polar.
They're both non-polar. So this one is, hopefully by now, a little more obvious that it's non-polar. It's carbon and hydrogen. And for the last few slides, we've been saying carbon hydrogens are non-polar. But this is carbon and chlorine. Why is that non-polar? That looks very polar. So initially, it would look like that would not dissolve in there. There's no oxygen.
It only has one carbon.
No? Why is CCl4 non-polar? tetrahedral, perfect. That is that special circumstance where everything cancels out. So even though the bonds are polar, the molecule is non-polar. And so CCl4 is soluble in C6H14 because they are both non-polar. If I added water to this, it would not dissolve. You might see somebody with a, I don't even know what you would, some sort of glass bottle, I guess, sitting on their kitchen windowsill with oil and vinegar. I don't know whether they use it or if they're just trying to be artsy, but this is what they have. There's vinegar and oil. Why do they not dissolve in each other? Why do you get that clear line separating the two? What is vinegar? It's acetic acid, but vinegar that you eat and that you buy in the store is not pure acetic acid. It's a small amount of acetic acid dissolved in water. So basically what you have is water and oil. The acetic acid itself is polar, so that wouldn't dissolve with oil either, but most of what you have here is just water. And so you get a nice little sandwich. We take this and we make a general rule. You may have heard this before, but we say that like dissolves like. And all this says is that polar things dissolve polar things, non-polar things dissolve non-polar things. And so if you have an ionic compound is very polar. It's as polar as you can get. So it will dissolve in a polar solvent. It will not dissolve in a non-polar solvent. If I put sodium chloride in olive oil, it's not going to dissolve. If I take a polar solute that's non-ionic, like acetic acid, and I put it in a polar solvent like water, it dissolves. But if I put acetic acid directly in the oil, it would not dissolve. And a non-polar solute, like oil, will dissolve in another non-polar solvent, but it will not dissolve in a polar solvent like water. So polar dissolves in polar, non-polar dissolves in non-polar. Which of these two do you think would be more soluble in water? Why the first one?
Because for me, the second one is,
Right. You have iodine bound to iodine. One element bound to another atom of the same element is as non-polar as you can get. So that is very non-polar. And this is not, while it's not incredibly polar, there is this oxygen here. And that oxygen is bound to carbon and hydrogen, and those are polar bonds. It is not symmetrical. That's methanol. Methanol is soluble in water. Methanol will dissolve in water, iodine as well. You'll do this exact thing in the lab in a week or two. Which of these two do you think would be more soluble in benzene? Benzene is C6H6. Second one. Benzene is a six-membered ring. Each of these points is a carbon. So you have carbons with hydrogens and single and double bonds. That's all that is. It's basically circular. That is very, very, very non-polar. And so the iodine, I2, is the more non-polar of these two, so it will dissolve in this. You already know from your life experiences that temperature affects solubility. If I want to dissolve something, what do I do with the temperature?
Increase it.
I increase it. Generally, the more I increase the temperature, the more I can dissolve. This is a generalization. Most ionic solids are more soluble in hot water than in cold water. You have to flip it around when you're dissolving gases in water. Gases are less soluble at high temperatures. Gases are more soluble in cold water than hot water. And we'll come back to that. So this is a graph of different gases dissolving in water with temperature. So here we have oxygen, nitrogen, and argon. At any given temperature, let's say 10 degrees Celsius, there is a very large difference in how soluble they are, right? But as we heat that water, it all starts to come out of solution, and at 100 degrees Celsius, at boiling, there's very little of any of it left. So this is showing us that gases are more soluble in cold water. You can get more gas dissolved in that water at a cold temperature. This is what happens, especially in the shallow lakes around here in the summer. Fish need oxygen, right? If fish doesn't have oxygen, it dies. But imagine you're a fish and you're in this thing of water. You're at 30 degrees, well, let's say it's a happy 15 degrees Celsius. You have a bunch of oxygen. The temperature decreases up to 30 degrees, which 30 degrees is less than 100 Fahrenheit. It's still not that hot. You have a whole lot less oxygen. And so as it gets warmer and warmer and warmer, the oxygen starts coming out of the lakes. And if it gets low enough, the fish will start to die. The way I remember this, okay, and this is probably not going to help any of you, but if it does, great. And maybe you'll remember my example and it will help you, okay? I'm a bass fisherman. I fish in tournaments. My boat has what we call a live well in it. It's basically an aquarium built into a boat, okay? So I catch the fish. They're not allowed to die. I get penalized if they die. I put them in that live well. And they have to survive to the end of the day because you win by having the most weight at the end of the day, okay? In the summer, in order to keep those fish from dying, I have to put ice in that live well. So I take big things of ice in the boat with me to continuously put ice into that live well to keep the water cold. If the water stays cold, I keep more oxygen in the water. Okay? So that is how I remember whether gases are more soluble in hot water or cold water. I actually stop and think about what do I physically do to keep the oxygen in that water, and what is that doing in terms of the temperature and the solubility.
Is that why fish like springs so much? Because they're like at a constant rate of temperature.
Yeah. So places around here, say the Santa Fe River, there are a lot of springs that go into the Santa Fe River. In the middle of summer, a lot of times the fish will congregate around the springs because that water is colder. There's more oxygen in that water. Another thing that affects gas dissolving in water is the pressure of the gas. And so if you have water or a liquid and then a gas above it, some of that gas up here is going to dissolve in the liquid down here. And the higher the pressure your gas is, the more it's going to dissolve down here. This only applies to gases dissolving in liquids. This does not apply to liquids or solids dissolving in liquids. If you change the atmospheric pressure, how much salt or sugar you can dissolve in the water is not going to change at all. So if we look at this in terms of a gas, the higher the gas pressure, the higher the solubility. So if you increase the pressure, you get an increase of solubility in a gas. So you can make a gas dissolve in a liquid by increasing the temperature, the pressure above it. So here we come back to our little piston system. In our pistons we have some water down here and a gas. And it's sitting there, and there is some of this gas that's dissolved in that liquid. It'll just automatically do it. If I take this piston and I push down, what happens to the pressure in this gas here? Does it go up or does it go down? It goes up. If I compress that gas, the pressure goes up. And when I do that, the pressure goes up, which increases the solubility of the gas in the liquid. So we get more of the liquid dissolved, we get more of the gas dissolved in the liquid. You are essentially pushing that gas down into the liquid. So, take that and explain to me what is going on with your soda bottles.
When you open it, it explodes because it's like the pressure's tight in there.
The pressure is tight in there, so when you open it, you release the pressure, all right? If you release that pressure, what then happens? The solubility decreases, so you get bubbles. The way they get the CO2 into the soda is that when they put that cap on, they have a very high pressure CO2 hooked up to the cap. And so, if it's a very high pressure, you get a lot of CO2 dissolved in the soda, and they cap it. And so, if it's capped, the pressure in that little bubble at the top is the same pressure as the system when they put the cap on. It's very high pressure. When you take that cap off, the pressure in that little bubble goes from their pressurized system to atmospheric pressure, which is a whole lot lower. And so the solubility of the CO2 in the soda decreases. If the amount of CO2 that's currently in the soda is no longer soluble, it can't hold that much anymore, you get bubbles. And so if you say you have a 2 liter, and you want to use it multiple times, how do you keep it from going flat? You put the lid back on, right?
Turn it upside down.
Does that work?
Yeah, that really works for me. If you turn it upside down and flip it back up, it's like it expands out, that air goes up, it keeps it from going flat.
We're gonna have to think about that.
That might actually make sense because you're putting more pressure on the caps.
It does work, trust me, it works.
That actually makes sense.
Right.
That's life experience trumping science, right? So, that's obviously the biggest thing you can do is put the cap on, right? If you don't put the cap on, you're toast, right? What happens when you put that cap on? It keeps whatever's in there. Right. And so, imagine you take the cap off, and this little space here becomes atmospheric pressure. It's low pressure, right? And you get all these bubbles here. And you put the cap back on,
You got a ball.
When you put the cap back on, the CO2 is going to come out of solution. You're going to get bubbles until you get an equilibrium. You reach a new happy place. And so the CO2 will make more pressure up here. That probably wasn't the first time you took that cap off, was it? And so the first time she took that cap off, she got a hiss. But then she put it back on, and the next time she opened it, she got another hiss. The soda repressurized the top. And so every time you open that, you're going to lose more and more CO2, and the happy place pressure is going to get lower and lower and lower, and so you're going to slowly lose the CO2 out. Another thing you can do is if, say your bottle is half empty, if you squeeze it until it's basically the liquid's about to come out the top before you put the cap on, you now have less dead space in there. And so the CO2 from the soda has less bottle to fill. And so more of it stays in your soda. Does that make sense? Because that is what we're dealing with, but in something that you have played with your whole life. So this also affects scuba divers. And yes, there's a scuba diving cat. Do we have any scuba divers? One. So, what do you know about coming up from the depths?
You have to go very slow.
You have to go very, very slow. What happens if you don't? You get the bends. And so, someone explained that to me in terms of gas solubility. What is happening? Why does she have to come up slowly?
You get too much carbon monoxide.
I think mostly nitrogen.
Yeah,
But
never
you
mind.
get too much gas. You get too much gas.
Yeah.
And so when you go down in the ocean, or wherever you're scuba diving, what happens to water pressure? Water pressure gets higher and higher and higher the further down you go. And so you're getting higher and higher and higher pressure. So that makes the gas that you're breathing more soluble in your blood. And so you get more gas dissolved in your blood. And so if you come up quickly, that the pressure on the outside quickly goes from high pressure to low pressure, what happens to you? That happens. Basically, you get a hiss and bubbles forming. But it's not in your Sprite bottle, it's in your veins. And that's not a good thing. Right? So that is the bends. When they come up, the gas comes out of solution and they get bubbles in their body. Do you know what happens if you get the bends? How do you fix that?
You gotta go in the chamber, gas chamber.
You have to go in the hyperbaric chamber, which is very high pressure. And so if I'm scuba diving, well, let's just go with the cat. Say the cat's scuba diving, okay? And the cat gets attacked by a dogfish, and it has to come up very quickly, okay? That cat gets the bends. I'm gonna take that cat, if I really, really love that cat, I'm gonna take it to the hospital and put it in the hyperbaric chamber. That's going to put the cat back at a high pressure. The bubbles in its body will redissolve. And if it redissolves, then I can very, very slowly bring the pressure back up to atmospheric pressure, so that as the gases are coming out of solution in the blood, the cat will just exhale them. Instead of getting bubbles, the cat just exhales the extra gas. Okay, so those are properties of solutions. But we can never leave anything in science to just words. We have to put numbers in everything, right? So we have to measure solutions. And what we're going to do is we're going to measure what we call the concentration of a solution. And what that concentration tells us is how much solute there is in that solution. Generally, when we're dealing with solutions, what we care about is the solute. We don't care about the solvent. The solvent, it just makes the solute more convenient to deal with. So the concentration is the amount of solute compared to how much solvent there is. We're going to have a number of different ways that we can talk about this. When we talk about concentrations, we have what we call a saturated solution. A saturated solution is a solvent that contains the maximum amount of solute that it can hold. So you know that if you try to dissolve sugar in water, eventually you're going to hit a point where it won't dissolve anymore, right? You add more and more and more and more, and eventually it will stop. That is a saturated solution. An unsaturated solution just contains something that's less than that maximum amount. So the solubility of something describes how concentrated a saturated solution is. And we give that in the units of grams of solute divided by grams of solvent. So we said earlier that solubility was how well something dissolved in something else. And so if we use an example and we say, we'll start with salt. Salt is very soluble in water. And so let's say you get 1 gram of sodium chloride dissolved in 1 gram of water. And then we go to something that we said was insoluble, like oil. Oil is not going to dissolve very much. You're going to get basically 0 grams of solute in your 1 gram of solvent. So that is literally telling you how much solute you can dissolve in X amount of solvent. Then there's a third special case. There is actually what we call a supersaturated solution. This is the rebel of the group. It doesn't go by the rules that chemistry said you cannot put more solute than this. It has more solute in it than a saturated solution. This only happens in very special cases. Usually what happens is you have something and you have a solution and you heat it up. When you heat it up, all of a sudden you can dissolve more in it. And so you get what at this point in time is a saturated solution. But when you then let it cool, the temperature comes down, the solubility decreases. And so what's dissolved in there has to come out of solution. But for something to come out of solution, it has to have a surface to form a crystal on. And so if I take a flask and I heat it up, let's say this is water, and I put sugar in it. This is basically boiling water, and I keep putting sugar into it until it will no longer dissolve. And then I take the heat off of it, and I let it cool to room temperature. If I don't disturb that, and I'm lucky, it may get all the way back down to room temperature, and there would be no sugar crystals that form. But if I take what we call a seed crystal, just one little crystal, and I drop it in there, then crystals start to form on that crystal, and they form and they form and they form until the solubility, how much dissolved, comes back down until it gets to that solubility limit, and then it will stop. Has anybody ever made a rock candy? Anybody? One. Do you remember how you made rock candy? What you probably did is basically this. You took water, you dissolved sugar and food coloring in it, and you got it really hot, and you dissolved the sugar until it wouldn't dissolve anymore. And then you put a string hanging down into that, and you let it cool. In your case, instead of a seed crystal, you had the string. And So when these crystals formed, they formed on, and so when you finished, you pulled the string out, and there was a bunch of sugar crystals on there, which was then candy. So this is a graph showing the effect of temperature on solubility. And we said that for the most part, when you heat something up, when you heat the water, you can dissolve more solute in it. Sugar follows that rule very well. As temperature goes up down here, the amount of sugar that we can dissolve goes up, which is why you can make that rock candy. Believe it or not, the biggest exception to this rule is salt. Salt has the same solubility in water no matter the temperature. You cannot make more salt dissolve in water if you heat it up. So this is how we can take this information and make a problem out of it. So this tells us that the solubility of sodium chloride in water is 38 grams in 100 grams of water at 25 degrees. This means that if we have water at 25 degrees Celsius, which is room temperature, for every 100 grams of water that we have, it can hold 38 grams of salt. The question then tells us, if this is the solubility of sodium chloride, and what I actually do is add 45 grams of salt to 150 grams of water, is it unsaturated, saturated, or supersaturated? How do you want to go about doing that? There are a number of ways you can do this. Some of them mental, some of them mathematical.
Couldn't you just find out the percentage of the first one and find out the percentage of the other and then see how they match up?
I think so, if I understand what you're, so what math would you do?
It's 45 by
Jamie wants to go 38 grams divided by 100 grams,
Right.
and then 45 grams divided by 150 grams. So that comes out to be 0.38. What does that come out?
0.3.
0.3. So now you've got that. What do you do with that? It's unsaturated. How did you know that? Right. So what this is telling us is the ratio between salt to water. So if we have more salt, this number goes up. And so this, it told us, is the solubility. This is the limit. This defines a saturated solution. If we find the ratio for what we actually have, if it's a smaller number, that means we have less salt. If we have less salt than a saturated solution, it is unsaturated. Another way you could do this is to take this and say, well, if I just take a portion of that, so that I actually have 100 grams of water, how much salt do I have? And so in this case, 150 is 1.5 times 100. So if I want to take this down to 100, I need to take 2/3 of that, which means I need to take 2/3 of that, which is 0.3. So, yes.
Could you do just add 50 to the 100 And then since that's adding half of the hundred, like, so then you would add half of
Correct.
45 to 30.
Correct. So the way she's doing it there, she's saying, well, let me figure out how much I can dissolve in 150, and then compare that how much I actually did dissolve. And so by doing that, she's saying, I have 1.5 times the volume. To go from 100 to 150, I have to multiply by 1.5. So let me take 1.5 times that number. What is 38 times 1.5?
57.
57. So that means that the solubility of salt at 25 degrees is 57 grams in 150 grams of water. So then you can compare that to this. And so this says that we can dissolve 57, but we only dissolve 45. So we haven't hit that maximum yet. So it's unsaturated. So there's a number of ways you can do that. Hopefully one of those makes sense to you. Anybody hung up?
A quick question on how you got the 57 grams out of the 150. Did you just multiply?
38 times 1.5.
In the case being 150 grams is the 1.5.
Correct. In order to go from 100 to 150, you have to multiply by 1.5. Right? Do you see that? So 150 is 1.5 times that. So you could take 150 divided by 100,
Yeah.
and you're going to get 1.5.
Oh, okay.
And whichever number you get, you then have to multiply your 38 by. So in this case, you got 1.5, multiplied by 38, you got 57. So, when we were in lab, I think last Thursday, one of the questions everybody was asking was the lab wanted, I believe, 0.5 m HNO3, and you had 0.1 m HNO3. And so we're going to talk about what that m means. When we talk about concentrations, we can put measurements on them. We can do more than just say unsaturated, saturated, or supersaturated. We can tell you, we can write exactly how concentrated they are. And there are 6 different measurements that we can do. We're going to go through each of them. So percent by mass is the first one, and it is easy. Okay? Take the mass of the solute divided by the total mass of the solution times 100. It is literally calculating what percent of your solution is your solute. Here's an example. Where it's asking the percent by mass of acetic acid in vinegar, and that vinegar contains 2.7 grams of acetic acid and 122 grams of water. And so we need to take the grams of solute divided by the grams of solution, the total grams. So I have solute divided by total. So what is my grams of solute?
2.7
2.70.
gram.
What is my total?
2.70 plus 122.
Make sure you add the two together. It is the total mass. So it's 2.7 plus 122.8. 1.70 plus 122.8. 2.7 divided, what is
145.5.
145.5? And then
That's
that,
122.
21.5.
Oh, hold on, my bad.
5.5. What does that mean?
21.5%.
Thank you, you need 1.5.
21.5%.
21.5%.
I thought it was 2.15.
That makes more sense now.
Let me see.
Because that's not 20%. 2.15%?
Oh, yeah, 2.15.
Okay.
Sorry.
So it was just total gram, or solute grams divided by total grams. Times 100. Hard? No. There's another one. We're looking for mass percent of sodium chloride, where we have 10 grams of sodium chloride added to 50 grams of water. So what's my mass of solute?
10 grams.
10.0 grams. What's my total?
60.
60. 10 plus 50. 60.0 grams times 100.
600.
16.7. Not bad. Very, very similarly, we can do percent by volume. This is just volume of solute divided by the volume of solution. The math is exactly the same, but instead of grams, we use volume. But what this is telling us here is a little caveat. Before we were taking the grams of the solute plus the grams of the solvent to get the total grams. Volumes don't work like that when you're dealing with liquids. If I add 10 milliliters of water to 10 milliliters of methanol, I'm not actually going to get 20 milliliters. So in a situation like this, you're going to be given directly the total volume of solution. Here's an example. 205 milliliters of ethanol. And here's the key phrase. Insufficient water to give a total volume of 235 milliliters. So that means our total volume is 235. So what is my volume of solute? 205 milliliters. What is my total volume? 235 times 100 equals what?
87.2%.
87.2%. This one's actually easier than the mass because they can't make you add the two things together. They have to tell you to divide the number directly. Then we can kind of mix the two. We can do mass per volume. This mass per volume is a scientist's favorite unit to use, but it is not a good unit to use. This is not, it doesn't work out this well very often. The math just doesn't work out, and practically you don't want to use this. But the math is no more difficult. Instead of grams over grams or volume over volume, it is grams divided by volume. So in this example, we have 0.9, it says saline is 0.9% sodium chloride. And then it asks us how many grams of sodium chloride are present in 100 milliliters of solution. So this one's a little bit twisted. This isn't just asking us to take grams and divide by volume times 100 to get percent. What is it actually asking us?
The gram of the syrup.
Right. The unknown is actually that. So that means the problem has to give us that and that. So let's start with this. This has to be given to us. What is it? It's 0.9%. And then grams is what we're looking for. And so we have to be given volume of solution. What is our volume of solution?
100 milliliters.
100 milliliters. Then we have times 100. So we're just going to solve for grams. Yeah, so mathematically, hopefully see this just cancels.
But and mathematically that is correct, but that 100 times 100 isn't in millimeters, doesn't have to be the same, or it doesn't matter, essentially.
See that?
I was thinking of like multiplying each side by 100, getting grams, and then multiplying by that 100.
The hundreds will cancel out. The milliliters will not disappear. The milliliters show up over here. Because this 0.9% is actually grams per milliliter. And so we have grams divided by milliliter. And so grams equals 0.9 grams. So there are 0.9 grams of sodium chloride in 100 milliliters of saline.
Will all these formulas be given to us?
I don't think these are given. These are not given to you. They're not given to you, but I had to guess, without seeing the quiz in front of me or seeing the homework, you probably won't have to memorize the mass percent or the volume percent or the mass volume percent. It may be on the written homework, but if it's not in the online homework, you're not going to have to memorize it for the quiz or the final. I don't think they are.
Wasn't like percent composition easy like this too?
Yeah. Percent composition was, say we had percent sodium in sodium chloride. And so we took the molar mass of sodium and divided it by the molar mass of sodium chloride times 100. That's all that was. Okay, let's take a break here, and we'll start at 35 after on that clock.
Busy and sleepy. I almost supposed to sleep. I'm almost forced to. I'm so sleepy. I have to walk in around.
Please don't talk about it. You know how much it's
Where is sleepy?
I've been dragging all day. You've been really busy on the wall. Walking around. Yeah.
Oh,
Ladies and gentlemen, Board of State.
Is it like stop my registration?
Couple pictures. One of them is actually good.
That was over 95.
Yeah. He's really high,
Very in the gut.
but he's actually not as good as some of the other guys. He's just on it. He's a big, tall guy.
Yeah, I went over it
So
myself.
very fast. He has
And
control.
then she was like,
But they can work on that.
And so for us, currently, he is probably our third best pitcher, but he made the number one.
Who's the third best pitcher?
yeah.
Oh, yeah.
And then, no, she, I think she was, yeah, but this is not even number 5. It's just on down.
Okay, so I would use it.
Oh, no.
Yeah.
This is 1 point.
Oh, can you show us how to do
There's
that?
T1,
Like,
there's
former-
EB.
So there's my job.
LVP,
Is like,
LVP. Our calculation,
and then there's like the 3.
solve.
So in the case it's,
So like right now, I'm still doing stuff like that. But we did with automatic, I don't know which one it is in the box.
there's no change.
We got 300 rolls where he did it. Like, cause, he did it on the board, so.
The pressure there.
Don't put it down, so don't put it down, just say, I don't know, right, you don't got that.
I didn't even know how to work it out.
Yeah, it wasn't that much.
Yeah,
Like, I
yeah,
had
what
to
you
look
need
down.
is that, the place
I
is
just
one.
want, it was back.
0 Celsius.
Like, as from like people were saying about
So we have a pressure.
maybe Martin or something. No, that's not.
We're looking.
Indirectly.
Oh,
Molecules.
So, we do that.
and then what about volume?
One body.
And then this is technically our different molecules from those. But how do we convert this? Can you show me how you did it?
So, you just take it out, you know how, you do the conversion?
Let me see how you did it.
Well, like, I don't work out nothing, man, cause I was at home, so all you do is you just convert it.
Put it on the table. That's easier.
What is it, what's that number?
1.80 times 10 to the 24.
So you just take it.
The hydrogen H2 is
10 to the 23rd, one more. Because that's the avocados thing. Yeah. So that's how you do that. So just divide it. So now you divide it. So divide this.
Yeah.
Look at the.
Like that, essentially. Yeah.
So that's how you get it. Then make it one more.
Huge point, oh wait, 200
Avocados. So one more equals
I
that.
thought so, I just wasn't sure if I was gonna.
I get it. The last one.
Hey, so what do y'all get for this one?
That's fine.
You got 66 on that, what do you get? This is 11. You got
You haven't done it?
Yeah, if you gotta go to the city.
Oh, that's it.
Yeah. Oh, it's got to be the calendar set.
For three, the STP. So there's numbers in STP, meaning which is 0 degrees Celsius and 1 atmosphere.
It is.
And so you use, and for these columns, we're going to use that formula, the ideal gas law formula, which is PV equals nRT. So we have our pressure, which is 1 atmosphere. Our N, which is our moles, in this case, we have to convert molecules to moles, that'll be our number. And then R is that number.
Well, technically, no.
Zero. Yeah, and then T is our pressure, which is Celsius. We're trying to do that. Did you do that? No?
I only do it.
All the way down to 3? Okay, alright.
Hold on, let me look.
I have no idea.
Hold on, because you told me earlier it was a 5, I'm saying you round up. Hold on, let me look.
Yeah, okay, I forgot.
If you get the numbers over there, of the current and divide by that, and multiply that, and do 0.5.
So you get sulfur.
Your sulfur was 32 plus oxygen, which is 16
Times 3, which is 50 something. 50 something.
48.
48 plus 32.
80.
And divide by that. So do that in harder.
Oh, it's a CL.
CL. Okay. Ooh, okay. Good thing I know that. Okay, CL for.
Divide by
Okay, so we just do.
Where'd you get the 22.4 from?
That's what we're going to do. He says that's it.
Alright, so I didn't do 4 and 5. I'm going to do 6. So asking you which one did we use like hydrogen bond? Hydrogen bond. It binds with chlorine, hydrogen, or yeah, with nitrogen, hydrogen, because that hydrogen is bonding with the nitrogen. So it's, the first one you got right. Yeah.
So the next one is at.
This one it was no, you want to know why? Is it a carbon alone?
So,
Carbon is in the middle.
with this,
The hydrogen bond, that's the carbon bond attached to the carbon, so the hydrogen and chlorine never really touch together. That would be, yeah.
them on the front, on the phone.
Oh no, I was just thinking it's
No.
What's the problem?
Just pretty much just like what volume of each FTP. I know FTP, it's 0 degrees Celsius, and 1 atmosphere and so we have to use that formula since everything is just constant of T equals nRT. What's the formula? PV equals nRT. So the R is the 0.804 number, I think.
Rodney, which
So,
formula do you use?
all right, and we can use dimensional analysis. You know,
Right.
Yes.
I'm ready to
That's what I did right now.
Okay, we've got just a few more slides to get through today, and then we're going to stop. And so the last two measurements that we're going to do are molarity and molality. Molarity is the biggest one. If you only understand one of them, molarity is the one to understand. It's the one we're going to use in lab. It's the one you will use when you're dealing with patients. It's the one that I use in my work in lab. Molarity is the big one. Okay? So molarity, we mark with a capital M. And the fact that there's a capital M is important. Because next one we do will have a lowercase m. So molarity is a capital M. Molarity is calculated by moles of solute divided by liters of solution. This is a formula that is not on your cheat sheet, but that you will definitely need on the quiz and the final exam. So don't forget.
Hold on, leave that up there.
Yeah. So molarity equals moles divided by liters. So here's an example of how we use this molarity. So we have a solution. It contains 117 grams of potassium hydroxide, and it's dissolved in sufficient water to give a total volume of 2 liters. It tells us the molar mass of potassium hydroxide, so we don't have to calculate it on our own. It says, what is the molarity of this solution? So we need moles divided by liters. Are we given the number of moles?
No?
No. Can we calculate the number of moles?
Yes.
Yes. So how am I going to calculate the number of moles? What number up there am I going to start with?
117.
I have 117 grams of KOH. I'm going to convert it to moles of KOH. One mole of KOH is 56.11 grams. So how many moles of KOH do I have?
2.09.
2.09 moles of KOH. So my molarity equals 2.09 moles divided by,
2.
it tells us our total volume is 2 liters. So what is my molarity?
1.05.
1.05, and we say 1.05 molar. 1.05 with a capital M.
Yes.
And if you want to be exact or perfect about it, it would be 1.05 molar KOH. But I don't really care whether you put KOH. I really care whether you put the M. Yeah, the M has to be there. Okay, so that's molarity. It's just moles divided by liters.
1.045, so you round it as 1.05.
It's close enough. I would give them credit.
Okay.
So that's molarity. Molarity. There's also molality. Okay? Molality is used. It has good intentions. It really does. Someone said, well, I have molarity. This is moles divided by liters. the volume of a liquid changes very slightly with temperature. And so, the molarity of a solution is going to change slightly with temperature. And so they said, well, let me make molality. In molality, we have moles of solute, the same way, divided by kilograms of solution. Mass does not change with temperature. And so, we had molality. But, practically in a lab, this is a pain in the butt. Because imagine last week when you were doing, it said add 2 milliliters of this, to 10 milliliters of that, and 1 milliliter of that. Imagine instead of doing milliliters, you had to weigh everything out on a balance. You wouldn't have made it through. You would have thrown everything against the wall and walked out. And so, in reality, everybody uses molarity. It is convenient. Measuring something in a graduated cylinder is convenient and quick. Measuring something on a balance is not. Okay? So this is why we have molality. But you will probably, I don't think you'll ever use molality in lab. I'm not sure I'll ever make you calculate molality. But next week, we will use the concept of molality, which is why we had to talk about it here. Okay? So this is just an example of how you would calculate it. And so we have another solution of potassium hydroxide. We have 56.7 grams this time, dissolved in sufficient water to give a total mass of 248.8 grams. So here we have molality. Molality is lowercase m equals moles divided by kilograms. So we can just plug in our new mass of potassium hydroxide, 56.7. Potassium hydroxide is still 56.11. So how many moles of potassium hydroxide do I have? 56.7 divided by 56.11. .01 moles of KOH. And so my molality was 1.01 divided by total kilograms. Notice that it's kilograms. We cannot use grams. We have to put it in as kilograms. So how many kilograms is that? How do you convert grams to kilograms?
1,000.
Divide by 1,000. So 245.8 divided by 1,000 equals 0.2458. So that number is moles, 2458 kilograms equals what? 4.11. 4.11, and we call that 4.11 molal. Where the other one was something molar, this is 4.11 molal. It's a 4.11 molal solution. Does that make sense? They're all pretty much the same type of calculation. It's one thing divided by another. It's just what's on the top, what's on the bottom. Okay. We're going to stop here for today. This is where we're going to pick up next week. And so we had plenty of time